Oh, hello there. My name is Giovani Baramuli with student ID 24101-106-0075 and from Information Systems C class. Today, I will be explaining the concept of crossing number in graph theory using the graph K5 as an example. Let's get started. In graph theory, the crossing number of a graph is the minimum number of edge crossings possible when the graph is drawn on a plane. It represents the smallest number of intersections between edges that cannot be eliminated by rearranging the vertices. And why is the crossing number important? A smaller crossing number makes a graph easier to read and understand. It helps reduce visual complexity and improves the efficiency of graph layouts. This concept is commonly used in network design, circuit boards, transportation maps, and data visualization. Now, let's move on to an example. We will use the graph K5 to see how edge crossings can be minimized and how its crossing number is determined. The K5 graph is initially drawn in a regular pentagon configuration, with all 5 vertices placed evenly around a circle. All 10 edges are represented as straight lines. In this configuration, there are 5 crossings formed by the diagonal edges intersecting each other inside the pentagon. Analysis step. Each pair of non-adjacent edges, meaning edges that do not share a common vertex, is examined to determine whether they intersect. Out of C(45) possible pairs of edges, 15 are non-adjacent pairs. In the regular pentagon configuration, 5 of these 15 pairs produce crossings. The red points indicate the locations of these crossings. Vertex V4, highlighted in orange, is moved to the outer side of the graph configuration. Its new position is placed outside the triangle formed by vertices V0, V1, and V2. As a result of this repositioning, several edges that previously intersected can now be routed without crossing each other. Consequently, the number of crossings is reduced from 5 to 3. Vertex V3, highlighted in orange, is now repositioned to a location that optimizes its distance from the remaining crossing edges. The strategy is to place V3 in such a way that edges VANC and THOU no longer intersect with other edges, except for one unavoidable pair. As a result, the number of crossings is reduced from 3 to 2. By strategically repositioning vertex V2 inside the polygon formed by the other 4 vertices, one additional crossing can be eliminated. The configuration consisting of 1 vertex inside and 4 vertices outside is a classical approach for minimizing crossings in K5. As a result, the number of crossings is reduced to 1. The final configuration shows the single remaining crossing that cannot be eliminated. This demonstrates that CR(1). No matter how the vertices of K5 are repositioned, at least one edge crossing will always remain. Therefore, K5 is a non-planar graph. This property is inherent to its topological structure and does not depend on the way the graph is drawn. Conclusion. The crossing number is the minimum number of edge crossings in a graph drawing. The number of crossings in K5 can be reduced by repositioning its vertices. At least one crossing always remains, regardless of the arrangement. Therefore, CR1 K5 is a non-planar graph.